with that, I want to welcome Peter Rood, and I want to thank him and his company Glidepath for agreeing to give tonight's presentation. Peter has over 16 years of energy sector experience with over 8 years of energy storage experience. Most of Peter's work has focused on the development of renewable energy and energy storage projects throughout North America, Micronesia, and Australia, and has included all aspects of energy project development, construction management, project finance, and mergers and acquisitions. Over his career, Peter's work has resulted in over 1.5 gigawatts of operating energy projects, representing nearly $3 billion of investment. So we're lucky to have Peter give us a talk tonight, and his presentation is going to be on energy storage systems, not just battery energy storage, but other technologies. Some of them have been in use for over a century, and some are, being developed to become more practical and more economical, and are emerging technologies. And the key reason we need more energy storage, we need huge amounts of energy storage to enable renewable energy to be the transition almost completely off of fossil fuels. So we want to use renewable energy almost completely. And with the exception of hydropower is mostly steady, although that fluctuates sometimes with seasons as well. If river levels fluctuate, that can happen seasonally. So it's a long-term variation. But wind and solar, you can have, days where you have very little wind. You can have, you definitely at night, you don't have sun. And then there are cloudy days when you have reduced output. You have some output with cloudy days, but still not enough compared to what you would like. So energy storage is what bridges those lulls, gaps in energy production from solar and wind. There's other technologies too, tidal, that's suitable in some areas. Wave technology is something that's becoming more practical, and that's more steady, but that varies as well. So anyway, I want to welcome Peter, and if people have questions, I guess, Peter, you can let them know whether you'll take questions during your presentation or whether you want to wait till the end. And we did start the recording, so I hope that's okay with you. I believe I asked you this before, but I just want to verify that that's okay.
Yeah, that's fine. And also feel free to jump in with questions either virtually, or sometimes the raising hand thing works, and hopefully I'll see that. But yeah, happy to be here. Thanks for the introduction. Good to meet everybody, and excited to talk about all things energy storage. As Val mentioned, I've been doing energy storage for quite a long time. I started in compressed air energy storage and flywheel technology. So even though I think most of the energy storage things that people think about today are batteries, there is other stuff that I'll talk about and kind of share my experiences and kind of what we're thinking about as a company and where we see New York going. But I've been doing energy storage for a long time and doing renewables and other sorts of energy generation for my, basically my entire career. First, can everybody see the slides here that are coming up? It should be a little map of the US. So I've got a couple corporate propaganda slides to get through first. That's the past letting me do this, as I get to talk about us as a company. But I assume you can see a map of the country here a little bit, and then if you can, that means it's working.
We can see it. Thank you.
Perfect. Yep. So Glidepath was founded in 2013. I'm the Chief Development Officer, so I look after all of the work that our company does to develop new projects and advance the redevelopment of our existing projects and all of those things that kind of happen prior to construction. We have another part of the company that operates the projects. We were founded in 2013, so that makes us one of the, even though it wasn't all that long ago, one of the first standalone storage developers in the country. We got our start developing battery projects in and around the Chicagoland area, and the first of those projects were built in 2015. We've really grown since then. We are a primarily an energy storage company, but we do operate some wind generation and some solar projects. But most of our projects have some sort of energy storage component. So right now, as it stands today, we have 18 projects that represent about 100 or 446 megawatts. Those are all the orange dots on this map here. And of those, 3 of them are energy storage projects, and those are about 21 megawatt hours of storage capacity. In the works, so what my team really focuses on is our 65 plus projects of development. That's about 3 gigawatts of energy projects, and almost all of those are energy storage, about 11 gigawatt hours of projects. In New York is one of our largest energy storage markets, and we have 4 advanced projects in the Hudson Valley that are in construction now, early stages of construction, but in construction. Each of those projects is 20 megawatts and 80 megawatt hours of battery capacity. And then we have 2 larger projects, our Oakdale project here that we'll talk about tonight, and then a little bit earlier stage project called Wood Street. We are a small developer, so we're only about 25 employees. We have folks in the office here in Minnesota, which is where I live and I'm talking to you tonight from, as well as an office in Illinois, one in Colorado, and then an office out at our site in Guam. And we are a private equity-backed company, so we're held part of Quinnbrook Infrastructure Partners. It's a private equity company focused on zero carbon, no carbon transitional technologies. So we're one of 3 of their primary portfolio companies in the US. We're the storage company. They also have a wind development company and a solar company. And incidentally, one of our sister companies, Primegy, just a couple weeks ago, finished the last few steps and started construction on a 600 megawatt, 800 megawatt hour solar project in Las Vegas, the largest solar project in the country. So here are some of our greatest hits. So our key projects we have up in the upper left are Jake battery project in Illinois. That was our first project that Glidepath developed and was built. It's a 18 megawatt, I think 1 megawatt hour project. It's a very small capacity, but high power project. It was built in Joliet, Illinois, and has been operating since 2015. The upper right there is our solar project in Guam that's also been operating since about 2015. Lower left is a picture from about 2 weeks ago of a project we have under construction in Texas, a 50 megawatt battery project that's just about an hour southwest of Houston. And then the lower right there is our Waymark wind project in northeast Pennsylvania. Sort of our wind facilities out there. So I thought kind of to talk about energy storage, and please do feel free to jump in with questions. I assembled this presentation tonight from some new stuff, but also some pieces from other presentations we've done. So if something doesn't make sense or it seems to be transitioning weird, oddly, let me know and I'm happy to explain. But I thought a discussion about energy storage ought to start with a discussion about the grid. And I think for the folks in the call here, this may be new news or obviously maybe old news, but figure we get on the same page. And Glidepath and the work that I do is really focused on grid-based energy storage. So there's all sorts of energy storage that can be done at your home or behind the meter at an off-grid site. But the work that I do is really focused on grid-based energy storage. And in the US, the grid is really divided into 4 pieces. There's the independent generators in most areas, and in New York, they are independently owned generators. So those are the different entities that generate power. Obviously, fossil fuel power plants, nuclear, hydro, and thankfully a growing contingent of renewable operators. So those are all the generators. That's where the electrons come from. The generators convert some sources of mechanical energy or other sorts of energy into electrical energy. And then the transmission operator, and in New York, that is the New York ISO, the New York Independent System Operator. transmits that energy at high voltages from the generators to over long distances to where it needs to go. In New York, the system's operated by a third party called New York ISO, but the wires are owned by various utilities, but they're the high voltage transmission system. And then after transmitting it from the generators to across the state, it ends up at your local utility. That's who your who maintains the wires that go from the substations and from the high tension, high voltage lines, to homes and businesses and industrial customers, and that's I'll refer tonight to them as the load. And so right now, this is the typical arrangement of the grid. You have generators that generate power, electricity from various sources. They transmit it over a transmission system. And then there's a local utility that distributes it within their service territory, and then the customers and load consume the energy. So in New York, this is New York, obviously, and we have these are all of the power plants in New York. The different colors here mean different things, different sizes mean different things, but generally blues and greens and oranges, or sorry, blue, green, and yellow are renewable power plants in New York. And the other colors are non-renewable assets. By count in New York, there are far more renewable power plants than any other number of generators, but by a quantity, by the amount of generation, number of megawatt hours generated, still fossil fuels and nuclear make up the majority of power in New York. But these are all the generators. This is where the power is created. For simplicity, I've left them out, but there also are imports and exports and all that kind of stuff. But these are the generators. These dots here are the generators in New York. And then the next step is to then move that power around. So this is the high voltage transmission system, somewhat simplified, but this is basically the main conduits of moving electricity around New York. These orange lines, they're like the interstates, but for electricity. And then those transmission lines lead to these orange boxes, which are all of the substations in New York. So these are where the power that is being transmitted steps down to a lower voltage to ultimately be distributed. And then these are, I didn't put any names on here, but these are all of the different distribution companies. So all the local utilities across New York. There actually are almost 100 individual utilities in New York, although I think there's about 7 that make up the vast majority of the state's distribution. So that's how it works in New York. This is very complex, moving it from generators across transmission lines to substations, and ultimately to the customers. But it's easier to think about it a little more simplified in this diagram. And one thing that I think is up until really the last decade or so, with the exception of pumped hydro, everybody in New York and everybody in the country, there had to be an instantaneous balance across the grid. So without energy storage, whenever you turned a light on or whenever an industrial load started consumption or anything like that, that load had to be, that customer had to be matched 1-to-1 by a generator. And likewise, whenever a generator, whether it's a fossil fuel plant or a renewable facility, whenever that generator was generating electricity, that electricity had to go someplace. It had to go to a load to be consumed. There was no slack on the system. There is no slack on the system. So if there is not enough load to consume all of the generation that is being generated, the system operator has to reduce that generation amount. And likewise, if there's more load than there is generation, the system operator has to increase the amount of generation available to meet that demand. And there's very, surprisingly very narrow tolerances to how much of a mismatch there can be between those two things. And the grid has always dealt with variability. I think sometimes people try to point out that renewables, wind and solar particularly, are unreliable or highly variable, and because the wind doesn't blow all the time or the sun's not always shining, that the grid is just going to fall apart because, it can't deal with that. It needs a constant, nuclear plant running 24/7. And that's just not true. The grid's always dealt with an imbalance across the system, and traditionally that's been mostly made up of varying load. There's no, as a residential customer, for example, you don't have an obligation to keep certain lights on all the time, to always be a load. You can do with what you please. And so the grid operators have always been adjusting for those changes. And really the only thing that's really changed now is that the changes, the variability is coming from both sides, both generation and the load. But the system is designed to deal with those situations, and always has been. So as energy storage enters the mix, you're really talking about using those existing systems to adding energy storage to add a time component to all of it. So energy storage, at its very basics, all energy storage does is shift energy in time. So whether it's it's a mechanical type of storage like flywheels, or compressed air, or pumped hydro, or some sort of a chemical type storage like a lithium-ion battery, or a thermal storage like ice storage. All of those types of storage, which we'll talk about here in a few minutes, everything they do is really just moving energy across time. And there's just different ways of doing it, and there's reasons you use different systems, but all it is moving energy across time. And so you have short duration storage, which is moving energy in the duration of seconds and minutes. So that's really, shifting very small amounts of energy over small amounts of time, to help, immediately balance the system. You have kind of medium duration storage, which is as it indicates, you're looking at a couple hours of storage, and that's really about optimizing the system to make it more efficient in most cases. And then there's long duration storage that is really fundamentally changing when generation or load is being delivered or consumed, and you're shifting energy from one part of the day to the next. Now, not on here, but definitely, out on the horizon is ultra long or seasonal storage, which is instead of shifting energy, from the morning to the evening, or from the overnight hours to the midday hours, or that kind of interday shifting, you're talking about moving huge amounts of energy from the summer to the fall, or from the spring to the summer, those sorts of shifts. And there are technologies that can do that, but I think as an industry, we really talk about these three types of duration classes. And what does that actually mean? So when a project is providing short duration services, we're talking about power quality services. So when the grid operates, it's designed to really operate within very specific tolerances. So when lights turn on and off, or air conditioners kick on and off, those strain the grid a little bit, and energy storage can help alleviate that. The technical terms for that are called voltage regulation frequency regulation and voltage support. And if what those manifest as when you're at home, kind of with your lights on and everything, if you ever see lights dim up and down or flicker, that's usually the result of a disruption in the frequency or the voltage of the power coming to your house. And right now, the grid manages that by throttling often natural gas plants up and down. So there's the grid operator will automatically tell a certain gas plant to add more gas or reduce the amount of gas, which changes the generation, and that moves the frequency up and down, and changes the amount of generation by a very small amount. And what batteries can do is do that same thing, but do it much more quickly and at a much lower cost. Similar to voltage support, it's a little more complicated, but batteries can use their inverters to manage voltage on a given system. The other thing that short duration batteries can do is provide for renewable ramping and smoothing. One of the challenges that both wind and solar, but in particular solar has, is that as clouds and other disruptions come across the site, the modules, the solar modules, change their production, change their amount of energy they put out up and down very rapidly. At our solar project in Guam, it's a near constant change across the project as clouds come over the site. The production goes up and down, up and down, up and down, and often now with newer solar projects, energy storage is being used at the solar project to act almost like a spring to buffer that change, so that the grid and the grid operator and the utility are dealing with a smoother curve, and that makes it easier for them to integrate those renewables onto their system. In particular, in areas like islands or remote parts of the grid where there isn't as much support by other generation or other sorts of equipment, those impacts from solar can be particularly noticeable. And I think as distribution systems become, as roof mounted and residential solar and commercial solar becomes more prevalent, I think you'll see utilities adding more batteries to help do that local management of those facilities. And then medium duration. So this is kind of what I think right now, at least for Glidepath and for many other storage companies, this is what I would say is the bread and butter of the work we're doing now. And these are projects that are about 4 hours in duration. And this is really going at the heart of many thermal generation projects to replace aging oil plants and these peaking facilities that have been around and are probably well past their useful life, but are still economically incentivized to remain on the grid, providing peaking generation services. And as storage becomes more prevalent and lower cost and more reliable, we really are, as an industry, going after those peaking generation sources as a way to replace them with energy storage, where projects are really charging when there's excess energy, whether it's excess renewables in the evening or other types of resources that are not necessarily meeting load directly, charging the battery then, and then discharging that during the day when it's needed, and really that manifests itself, I think, right now in two ways. One, it's in areas where there is significant amount of solar generation. It's charging the battery actually during the middle of the day, so during the noontime peak, and then discharging that battery at various times in the afternoon and early evening, when most systems are starting to peak. And then it's also using batteries to shift wind. So in the evenings or overnight hours when it's windy, but there isn't much load, charging batteries then, and then dispatching it during the day. There's also reserves. So even today without renewables, just in a normal power system, the grid operator will maintain a certain amount of reserve capacity. So in the event of a generator failure or a transmission system outage, there are plants that are in some version of standby mode, kind of ready to kick on and fill that need. One of the interesting things with an increase in renewable generation is that with both wind and solar, the number of individual generators increases substantially. So a gas plant that may have 2 or 3 primary generators that if a steam turbine or a gas turbine goes down, that could be several hundred megawatts of capacity that's down until that generator is replaced. For with a wind plant or a solar facility, The individual wind turbines or the individual inverters, are the pieces that fail. And you can have a wind project that's 100 wind turbines, and even if one or two of those wind turbines are down, in almost all cases, the rest of the facility can continue operating. So as the grid evolves, it'll be interesting to see how the reserve requirements change over time. And then finally, the last thing you really see medium duration storage used for is grid congestion management. In New York, I think most of the utilities call these non-wires alternatives. So in the New York State requires, the PSC requires that utilities in New York, prior to building a new large transmission line or investing in transmission upgrades, they evaluate whether or not storage is an effective replacement. Prior to joining Glidepath, the company I worked for, Renewable Energy Systems, we actually installed a non-wires facility in Brooklyn for Con Ed that effectively replaced the need to upgrade an underground transmission line. So at a substation, we installed a number of batteries, and those batteries basically in periods of low use, those batteries would charge. And then as loads increased, when normally it would overload the transmission line and require a new transmission line to be built, our batteries would then discharge and would effectively replace that new transmission line. So batteries just really allow, or storage, I should say, in general, really allows the more effective use of the transmission system when installed in areas of high congestion. And then finally, the long duration. So what's coming is these longer shifts. So storing more energy for longer periods of time, and that really is moving renewables across whole periods of the day, removing large grid constraints, across state level facilities, and then as thermal plants remain, as the grid transitions away from thermal generation, but at least for the next decade or more, probably has some thermal plants remaining in the system. Energy storage can be used to optimize those thermal plants. For example, in Ontario, the grid operator there uses pumped hydro to optimize their nuclear fleet. And at night, instead of reducing the output of the nuclear facility, which is challenging and not very cost effective, they use pumped hydro to store that excess nuclear generation at night, and then discharge it when it's needed during the day. So that's kind of the uses. There's a couple of different ways, and I'll spend some time here walking through the different types, the different different mechanisms of doing energy storage. This is a good graph that the Department of Energy has put out. There's various versions of this, but all of in the bottom left is really the shortest duration, lowest capacity, and then as you move across the graph up and over to the right, you get larger capacity to the right and longer duration. So you see here the orange facilities, the pumped hydro and compressed air are really focused on very long duration, very high capacity use cases. In the middle, you have batteries, which is not surprising, especially given now that the batteries really seem to be the vast majority of applications. And then some specific kind of nuanced applications are scattered throughout. We got some capacitors that are used at substations, and then flywheels kind of in kind of two kind of small parts of the graph. Flywheels were I think an interesting part of the early stages of the modern energy storage movement, but deployment, but have not been all of that. You haven't seen too many flywheels being deployed recently as battery costs and reliability have come down. So looking at the technologies here, I think in my mind, or for a high level, we can kind of divide the technologies classes into two basic categories. The first two that I'll kind of walk through is the mechanical category. So this is where you're you're moving something, and that movement, that mechanical movement, is how you either store or discharge the energy. So the kind of tried and true, one of the energy storage technologies that's been around the longest is pumped hydro storage. So this is, using gravity to move water uphill to store energy, and then holding that water in a reservoir and discharging it when it's needed. So these have been around for a long time. There's one in New York. NYSEG has a project. This is a photo of it, and it actually just got reauthorized by the FERC. So this project's going to be around for a while. But here you can see a classic implementation of pumped hydro, where the lower reservoir is the kind of baseline reservoir. I think that is it's part of a creek or a river of some sort that is the lower reservoir and has its own generation as water is let from that reservoir. But then at the top there's the upper reservoir. So to store the water is pumped from the lower reservoir up to the top to the upper reservoir, and it can sit there for as long as it's needed. Whether it be some pumped hydro operators use them on a daily cycle. So every evening they pump water uphill, and then during the day they let it downhill and discharge it. Other operators have a more complex operation where they use it over longer periods of time. Really depends on what the grid operator needs in that moment. But pumped hydro projects have been around for a very long time. They have both high energy, so they're usually several hundred megawatts, if not gigawatts worth of generation capacity, but also very long duration. So these the reservoirs are very large and can hold a lot of energy. The challenge with building new pumped hydro, there hasn't been any new pumped hydro built in the United States for several decades, is the cost. So these are extremely costly projects to build, and the impacts the projects have both to the environment and to the community. These projects, cover a lot of land and require both federal and state level approvals, not to mention the land rights and acquisition required to secure the property required for these types of plants. There have been some folks that have tried these projects. There's a group in Pennsylvania working to permit a pumped hydro facility in northeast Pennsylvania, but so far there doesn't seem to be any really in the near term. Other sites of mechanical storage is very similar, is compressed air. I have personally a lot of experience with compressed air. I worked for several years at the compressed air company trying to develop a new compressed air type of technology. And compressed air is very, very similar to pumped hydro, but instead of using water, you're using air, and you're compressing air and at high pressures into the ground and storing it either in salt caverns, so underground rock formations that are hollow, or in depleted gas or oil caverns where there was gas and oil that's been removed. So you compress energy or compress air when to consume or store energy, and that air is then kept underground. And then when you want to generate more energy or release that from storage, you reverse the system and move that air back through a turbine to generate energy. One of the challenges, as you may know, when you compress air, it often gets very hot. And when you decompress air, if you ever have one of those cleaners for your keyboard that you spray and it sprays out compressed air, it gets very cold. And so one of the challenges or one of the issues with compressed air storage is that you lose a lot of energy with the thermal dynamics of compressing and expanding the air. The outfit that I worked at for several years called General Compression, we had a technology that we were trying to capture that heat during compression and store it in a liquid, and then re-inject that heat during the expansion phase to try to minimize those losses. But ultimately did not not really get the technology to work, and I think it's been kind of elusive. There's been a number of companies that have tried to get compressed air to work, but have run into issues. There are today, even today, only 2 compressed air facilities in the country, or sorry, in the world. There's one in Alabama and then one in Germany, and both facilities use natural gas to aid in the cycle. So and they're both built, I think, in the 70s or early 80s, and nothing new has really come about. But definitely a technology that I think is interesting, because it like pumped hydro allows for very high power, very high energy, and you can store a lot for a long period of time with the facility. On the other side of things is our flywheels. This picture actually is from a flywheel facility that I built in Minto, Ontario. It's the Temporal Power Minto facility. Unfortunately, Temporal Power, the supplier of these flywheels, is no longer in business, and I think that is probably indicative of how the technology has progressed. Flywheels have a big spinning mass that when you want to store energy, you spin that mass up, and when you want to discharge energy, you engage a generator to slowly add resistance to slow that mass down. And flywheels are used kind of all over, as that same concept is done in various mechanical types of machines. Farm equipment traditionally uses flywheels sometimes to help maintain speeds. But for energy storage, electrical energy storage, it is not proven to be a cost-effective or ability. It really has not been able to compete with batteries. One of the challenges with flywheels is to get efficiencies that work. The flywheel, inside that silver tube there, or silver kind of barrel, needs to be maintained at a vacuum. And so, in addition to the mechanics to spin the mass, there's a whole system required to maintain a vacuum. So all of the flywheel systems, maintaining the vacuum is a large kind of piece of the project. And of course, there's a bunch of moving equipment, so that all gets hot, and that heat needs to be managed as well. And so flywheel projects often have both high installation costs and costs associated with installing the projects, but then also a high operation cost, because all of the pieces of equipment, the spinning pieces of equipment, as well as all of the support, the cooling and the vacuum machinery, all needs to be maintained, and that adds to the operating cost. They're also just kind of difficult to work with, because you notice here in this picture, there's lots of concrete. What's not shown here are the big 18-inch concrete lids that also need to go on top of these things, because the mass is so large and is spinning with a lot of energy, which is the whole point. If something goes wrong, you have a big, several ton piece of metal spinning around that you need to contain. So these facilities have lots and lots of concrete, and that's what's shown here where they're standing. And then, like I said, there's a big concrete lid that goes on top of these things. But the Minto project that we built in Ontario we built that project in 2013, 2012. I did, that project's going strong and providing frequency regulation services to the Ontario grid right now. And as far as I know, is still going really well. Last type of mechanical storage that is worthwhile to talk about here is this gravity-based storage. And this is a pretty broad category. I chose this one because it's located next to one of our wind facilities. This demonstration is located next to one of the wind facilities that we have in California. This is a rail-based technology where to store energy, they move what essentially here is a big concrete block up a hill on a rail system. And they use electricity to do that. And then when they want to discharge electricity, they the weight goes down the incline, and uses essentially regenerative power to feed power back onto the grid. I actually think that these guys use essentially subway car motors, so that very similar type of electric motors as subways and even most electric vehicles now, where they can operate in both directions. And instead of using brakes like brake pads, they use resistance, and that resistance turns into electrical energy. And here, instead of like a Tesla putting that energy back into the battery, here it's going right on the grid. So that this is a prototype that I know has been supported by the Department of Energy, and I think is still in ongoing development. There's also another outfit that also uses concrete, but instead of going up an incline on rails, they use a crane system to move it around. They've gotten some press with that, doing with some investment recently. So I think the gravity storage potentially has similar potential that compressed air or pumped hydro does, where it potentially could have a lot of power very cheaply. I think the downsides that for Glidepath at least, we're watching from a distance and not getting involved yet in any gravity storage projects is well, twofold. One, most of these technologies are still we're still earlier mid in their development cycles, so it's a while before they'll be on the market. And also I think that there's similar concerns as flywheels, that they have lots of mechanical parts, and similar to pumped hydro, most of them need quite a bit of space. And I think also from a carbon and ESG standpoint, concrete in and of itself, both this train system and the guys that use a crane to move blocks around, both use lots and lots of concrete as the kind of low cost way of adding mass to move up and down. And concrete, at least today, the typical supply of concrete is not a very carbon efficient or carbon neutral source. So not nearly as bad as burning fossil fuels, but definitely not insignificant, and would need to be considered as part of projects that involve concrete. So that's kind of the mechanical types of storage. The mechanical types. The other part that I think is worth talking about here is the electrical and thermal. So thermal and electrical are using kind of chemical properties. So here we have a thermal salt project. So here they store energy in using the sun to heat up salt that's in this facility. This is out in California. These silver tanks here hold the hot salt, and then at night when there's no sun, they use the hot salt to heat a boiler and generate steam and make electricity. Kind of the opposite in some ways is ice storage. So instead of heating up salt, you cool down water or liquid and make ice at night, but then use that ice to cool a building. The Empire State Building, here is their system. So they use this ice storage system to provide cooling for the building. And there's actually a number of these implementations in New York City and elsewhere. That it seems to be a pretty good technology for large buildings. And then flow batteries. So flow batteries are a type of chemical storage where there's promising technology by moving the cathode and anode chemicals around across them in moving energy across the membrane to store energy in those chemicals. But kind of similar to some of the other mechanical storage, there's a lot of companies that are pursuing this, and definitely very interesting, but has not kind of crossed the commercialization bridge yet. So those are all of the past and future, at least that we're tracking. There's various iterations of these, different types of battery, different types of mechanical and chemical storage, but these are kind of the main categories that seem to be getting some traction. And that kind of leaves us then with what we're as a company, Glidepath is really focused on, which is lithium-ion battery storage. Unfortunately, not really, I don't have a lot to say on is other types of batteries. So there's historically the lead acid batteries, which are in most internal combustion engines and have been around for a long time. Those are, there was a small time when those were used for grid storage, but really have not been deployed, and there isn't really much research or work going on into lead acid batteries for grid storage. And there's different types of other chemicals, some versions of lithium ion. There's other types of ion-based technologies that are all in early stages of development, with various brand names. But lithium ion has really become the dominant near term, and for almost, I think last I looked, 90% of energy storage in the country that's been deployed, maybe 95 actually, is lithium ion batteries over the last 10 years. And almost all of the projects that are planned that I know of are use some version of lithium ion batteries. And the reason why is summarized here is that lithium ion batteries have been around since the 1980s. It's a relatively well understood battery technology, battery chemistry, much higher energy density. So per square meter per kilogram, you can put a lot more energy into lithium ion batteries than you can into, for example, lead acid batteries. And because of that, they've been deployed across different sectors. Lithium ion batteries have been in electronics for the last decade plus. Everyone has in their phone has a lithium ion battery, laptop computers. Almost every electronic device that you plug in to charge is using some version of lithium ion technology. And because of that, there's a very well developed supply chain and distribution network with very well established manufacturers. Unfortunately, not too many in the United States, but in Southeast Asia, Korea, China, Japan, making these batteries, and they're reputable manufacturers. They're reliable. They provide warranties and all those sorts of things, and have a great track record of providing relatively high quality batteries if you choose the right ones. And the market share. So as the scale and as technology improves, it's not just the grid electric storage, grid battery storage that's benefiting from that. There's huge markets that require lithium ion batteries or similar batteries. Electric vehicles and electronics, as I mentioned, all are huge drivers of demand here. Lithium ion batteries have a relatively strong safety record. There've obviously been high profile incidents with all types of lithium ion batteries, electronics, vehicles, airplanes, standalone batteries. But overall, considering how many lithium ion batteries are deployed, the track record is very good from a safety and risk management perspective. And there's a growing and improving network of recycling and reuse that we're seeing in the United States. Glidepath is, we have a program where we track every single battery cell in our systems from manufacture to disposal. And disposal includes, for almost all of our projects, a repurposing of the battery, recycling of the raw materials, and disposal of the battery container. And of course, they're getting cheaper and are a low cost and cost effective solution. So grid-based, kind of getting to the end here, the grid-based battery storage systems. So what Glidepath does, what we do. This is a picture of our Myersdale project. So this is a very typical grid-based battery system. Basically in the white kind of mobile home looking type things are where the batteries are. There are some inverters and transformers and then a large transformer that sends the power up to the grid. And then here's a kind of a schematic how it works. So a grid battery project takes instructions and other signals in and uses a control system to manage the charge and discharge of the batteries. Batteries operate as direct current, and so they have to go through an inverter to change that direct current to alternating current, which then goes through a transformer and then ends up back onto the grid. So a standalone battery project has this schematic here is basically what those projects look like. In a practical standpoint, this is a picture of our Prospect project in Texas. You can see kind of the same thing. So you have the batteries in the shipping container type structure. There's a bidirectional inverter, so there's a white thing here that converts the DC battery components or DC from the batteries to AC, and then there's a transformer to then step up that AC voltage to the grid voltage. And then kind of looking at it a little more, kind of diving into these things. This is the inside of those containers. So this project we built a couple of years ago uses batteries supplied by a Canadian company called Powin. So inside each one of these, there's stacks and stacks of these batteries, and they're loaded in there like a computer server rack almost. And then here's kind of a close up. So these are the individual batteries. The battery modules are kind of what's slid in here, each one of these little things in the rack. And then here's a blown up view of what that looks like. And inside of that is the battery cell itself. And the battery cell is kind of the core of the kind of core Lego, core building block of the whole project. And when you talk about a big utility scale or grid connected battery, it's really just connecting, thousands and thousands of these battery cells into modules, into these racks, and putting the racks in containers, and then connecting it all up as a project. So those projects. So our Oakdale project. So this is the project that we're developing in New York. Our 120 megawatt Oakdale project. So kind of starting with why we're doing this. So New York has a very aggressive climate goal, with a goal to have 70% of load served by clean energy by 2030, 6,000 megawatts of energy storage by 2030. That's just less than 8 years away. And of course, zero electrical grid emissions by 2040. And, so that's the policy reason why we're doing this work. But it's not just policy, there's also reliability and economic reasons. The cost and reliability and accuracy of batteries is, even without policy drivers, is giving traditional incumbent thermal generators a run for their money on competitiveness. So the grid services that balance the ups and downs, batteries can provide those cheaper and more reliably than thermal generators can. We're also integrating renewable resources like wind and solar and providing clean peaking capacity. The Oakdale project is located just north, or it's in Johnson City, so just northwest of Binghamton, adjacent to a NYSEG substation. The project will be about 120 megawatts, 480 megawatt hours of capacity. So about 4 hours of capacity to discharge at when it's fully charged. Our permitting is materially complete, so we've received all of our local land use permits and site plan approvals. We need some administrative building permits and that sort of stuff, but the project is well through permitting. We're currently awaiting interconnection studies from NYSO, which we expect to be done this year, which allows us to start construction next year and probably be in service at the end of next year. So kind of some different views here. Here's a little bit closer. You can see the NYSEG substations to the left here. And then our proposed facility is there kind of in purple. Our neighbor there, I think, does some sort of building material recycling or something like that. But it is kind of off the side and generally a open area here. There is a gas pipeline that kind of cuts across the side of the project there, which is that line kind of through the trees we're staying away from. Here's a site plan of it, showing, it will be just a large number of these containers, containerized facility, about 120 of these containers lined up in nice little terraces. So the area is sloped a little bit. So these will be stacked in terraces, kind of lined up one by one like that. The project should be pretty well hidden behind the existing trees. So here's some visual simulations we did last winter, between kind of coloring the containers a dark green or gray color, and the elevation changes and putting some vegetation. Expect this facility to be pretty hidden back there. Obviously in the summertime it'll be even more difficult to see, but we think this is kind of a relatively indicative view of how the project will look. And then what it does, so our Oakdale facility, will provide kind of 4 primary services. We'll provide capacity. So this is the long-term planning that NYSEG and others use to make sure there's enough capacity to meet the demand in the future. So that's kind of one of the services. And then we'll separately provide peaking generation. So when there actually is a high demand for power, often in summertime afternoons or overnight in the winter, we will provide that peaking as dispatched by the grid operator NYSO. We'll provide some of those reliability services that I mentioned, so called spinning reserve and frequency regulation. So, taking away those services from thermal generators and providing them more accurately and cheaper with our battery. And then we'll do in New York, we'll do kind of real-time energy trading. So what this effectively is doing is using economic indicators to charge the battery when there's relatively low cost of power, often when there's an oversupply of electricity, and then discharging the facility when there's an undersupply of electricity. So when the prices are high. Those are the primary services. So that's kind of what the business of our project is. With the Oakdale project, we'll have one customer. It'll be the grid operator NYSO, and these are the products it will sell to NYSO, and that's how we'll earn back the cost of building the project. The project is probably about a $200 million facility when it's all said and done. So the future energy storage in New York, we're working on other projects across the state, but it's a challenge. I think there's a lot to be done to meet the not only the governor's goals of 6,000 megawatts by 2030, but also to practically meet the needs to transition the grid to a no carbon grid by 2040. As a developer, we're running a business. So while we believe in what we do and we want to move our work forward to aid in this transition, there's also a financial aspect to it. And I think that one of the challenges in New York is because there is so much change going on, it's hard to see the real financial signals and get comfortable that investments we're making are the right ones. So we're advocating for more clear, kind of more cut and dry market signals, so that when we start investing in a project, our projects take anywhere from 3 to 6 years to develop. That we want to make sure that the market, that when we start developing a project is there when we get done. And right now in New York, there's so much change going on that sometimes it's hard to see kind of what the final state of the market's going to look like. And the market is, I think things are changing, but the traditional NYSO market is designed for a purely economic decision. So policies that it's hard for policy driven change to happen because, the system is really set up to really only focus on the lowest cost. And right now there is a cost to transitioning to low carbon, no carbon sources of energy. And sometimes those costs need to be reflected in the price, and that doesn't always work in how the grid works in New York now. The cost to develop in New York is long and expensive, which I think is one of the challenges with New York generally, but it's not as bad as it is other places. We're having longer and more challenging, especially permitting work in other states, and NYSERDA and other parts of the administration have done a good job in New York in trying to streamline the process and providing support to towns and counties. And I think New York is really leading in that right now with those policies. But the grid study process that NYSO runs is long and expensive, and provides a lot of uncertainty, for a project that's going to be in service and operating by 2030, which is the deadline and the goal. Those projects, need to be starting now. And if you can't start a project in 2025 and expect it to be done by 2030. So we really kind of are bumping up against the deadline for that 6,000 megawatt goal. And then finally, with all the work in New York that's going on to implement these low carbon changes, There is a lot of different agencies and different partners and different groups working on this. And I think sometimes there's not as much coordination as there could be to optimize where some of these facilities are going. So there's both distributed based generation, so residential solar, that kind of thing, onshore renewables and offshore wind. All of those things are happening and are making good progress. There's not a ton of coordination across those different things. And I think energy storage is a great way to help weave all of that together. Same with EVs, electric vehicles, and really looking for ways to figure out how to balance that demand on the grid, and how to use some of the new technologies from some of the manufacturers where the vehicles themselves can actually act as grid support batteries. And then finally, the kind of balancing between the grid, the distribution systems, and homes and businesses. There's different parts of NISO and the governor's office that manage those programs, and sometimes it's not always as coordinated as it could be. So I think I got most of that in about an hour. Lots of stuff, but happy to chat about any pieces that I cover that there are questions on, or happy to go back and dive deeper into stuff. But I appreciate the opportunity and the time.
Thank you very much, Peter. You covered a lot of ground, and I'm glad that you covered the gravity-based systems as well. Some of those have a lot of promise. People are making modularized systems where they want to raise standardized weights in a rectangular fashion that looks like, a rectangle if you look at it from the sky down, as well as each individual thing that you're raising is also rectangles. Yeah. So this is something that is very promising, and those weights don't have to be concrete. They could be something else too. You could have baskets of rocks, for example. The baskets could be standardized, and it could be enclosed. So there's different ways to do that. And I hope that people continue to work on that. But I'm glad that you verified what I suspected. I'm an engineer. I don't know if are you an engineer?
No, my background's in environmental science.
Oh, okay. Well, you're in the right field. I'm sure that you sleep much better at night doing what you're doing, because this is a very important thing that you're working on, and it's really helping the world. It's not just New York State and the other states that you have projects in across the U.S. and a few places outside, like Guam you mentioned, but you're helping to move the needle in the correct direction. And what I'm trying to get to is that I am an engineer. I'm retired, and I looked through, at least scanned, especially the grid portion of the Climate Action Council's draft scoping plan for New York on how they plan to transition to renewable energy for the state. And I agree with what you said. I'm glad you verify what my suspicion and other people's suspicion is, that there's seemingly not enough coordination and planning. They're sort of expecting the market to magically make this happen. And I don't think that's good enough. And what you said about the timelines and the costs being long, I'm really surprised that the New York ISO is going to take seemingly possibly a year to finish identifying whether or not your project is appropriate to hook into the grid here. I mean, I don't understand why is that a complicated thing to figure out? They've got two big substations diagonally across from where your site is. They've got the high voltage transmission line right there. We know that this storage is going to be needed. We know that it's going to be orders of magnitude more than this project is going to be needed in New York State. So I don't understand why this should be a delay.
Yeah, it's challenging. It's not unique to New York ISO. For almost all of our projects universally across the country, the process to get permission to connect to the grid is the longest piece of the process. And I think what universe kind of this at high level, what I think what it boils down to is the cost to connect is usually millions of dollars, and there's overlapping federal and state laws that talk about how those costs are to be allocated. And NYISO and other grid operators have a very stepwise and deliberate process to calculate that, which makes sense. I think what complicates it is that the way they calculate it is that it's not just a 1-to-1 ratio. So if we're connecting to the Oakdale substation and our project causes an overload, for example, of a transformer, but there are also other projects that are causing part of that overload, there's an obligation by NYISO to allocate those costs between all of the projects. And as you can imagine, when people are asked to share costs, there's not always agreement. And so that is often what takes a long time is working through a process to fairly allocate those costs. What they do in Texas, which is unique, and one of the reasons why ERCOT, as people may know, has all sorts of problems with their grid. But one thing they do very well is they socialize the costs of those upgrades. So our projects in Texas, they have to be studied to figure out what's needed to connect them. But the cost of adding those facilities to connect the project isn't borne by the project. It's allocated to the rate base. So all of the users of the Texas grid pay for those costs. And that's one of the reasons why our projects in Texas take about 8 months to develop from the time we sign up the landowner to the time we put the first shovel in the ground is 8 to 12 months. And in New York and almost everywhere else, like I said, it's not a unique New York issue. It's several years. And part of the reason is that the way they do grid connections in Texas is just so much more efficient, which is interesting because of all the I think common views on Texas about socializing costs. You wouldn't think that's where they would have it figured out, but right now, that with the grid, at least, that's how they do it, and they do it well.
Okay, thank you. It's still very frustrating to me. I think New York needs to push and standardize what's done so that this can be done much faster, and definitely even at a higher level. The other major question I want to ask you is, follow-up question to this is, do we need more legislation in New York to be passed in some way to shorten this process and to also make it more financially practical and beneficial for companies to, it sounds like you're saying that you're not really getting any incentives. Your company is investing this money all on their own. Is that true with venture capital backing you up? Is that what's happening?
So our 4 projects in the Hudson Valley have received minor grants. They're not quite, they're definitely not covering the entire cost of the project. And, there's still a lot of risk involved. And, this Oakdale project is we're assuming that there is no incentive available for this project, which makes it more difficult. And, I think what I think New York needs to eventually start thinking about is as you may know, they have this, and it's not just New York. This is, a lot of the things that New York is a leader in transitioning to a zero carbon grid, but a lot of places are not far behind. And so I think, New York has the ability to kind of lead here and come up with some of these strategies. But one thing that really has revolutionized how renewable energy has gotten built is the idea of a renewable energy certificate. So this idea that in addition to the energy, there's a renewable energy credit that's generated by the operator, and that credit then can be valued independent from the electricity. And so the credit can be assigned a value by the government, by the state of New York, by utilities, or by third parties like Google or Amazon or someone like that. And I think what storage could really benefit from is Right now those renewable energy certificates are really settled on most cases an annual basis. So a renewable energy credit or certificate that was generated in 2022 is just a 2022 rec. And I think what needs to happen is as more renewables come online, it becomes more important as to when that renewable energy is delivered. You can't have every solar project delivering all of its energy at 1 in the afternoon. Some of that solar energy needs to happen at different times of the day. And same with wind. You can't have every wind project delivering all of its energy at 3 a.m. in January. And so I think what the state could really do is come up with a mechanism similar to a REC that really aligns, allows an energy storage project, whether it's standalone like our projects or independent, or tied to a renewable facility, to add value to a REC generated by a wind facility or a solar facility, add more value to that REC by storing it and then discharging it when it's actually needed. And so I think there could be a system that someone comes up with that does that. But that's a very new concept, or very, it's a big step forward. And so far, NYSERDA and the other policymakers have been, I think, hesitant to take that sort of drastic step, and have really been focused on kind of, a little bit of a grant here or some something that helps 2 or 3 projects over there. But the legislature, I think, could come up with something like a time-based REC that the state could administer and do essentially what they do with the RECs that are generated by wind and solar, which is provide kind of the incremental value needed to make that part work, that the projects need to make it work. So that would be I think, in my opinion, I think that would be a great way for the state to kind of jump out ahead and lead the next wave of these sorts of projects.
Okay, I thank you for that suggestion. I'm going to give you a suggestion. If your company hasn't already, I would suggest that you try to put together ideas on how you and your company would like to see New York's draft scoping plan changed. They're accepting comments until June 10th. And I think they desperately need to improve what they're doing with the electricity grid. And the other thing I'd like to ask you about too, which has been burning a hole in my head. I haven't really gotten a straight answer from New York officials yet. This 6 gigawatts of storage, to me, number one, it's in the wrong units. It needs to be time also. They need to specify that as well. And gigawatt hours needs to be specified too, which I think is even more important than just the total power capacity. And then the other thing is, what time phase is available? Is it what you're talking about for your company, the typically 4 hours? Is it the longer that maybe that can cover a whole day or perhaps a couple of days? Or does it even need to be weeks? Does it need to be months or even seasons? I think they need to have buckets of, okay, we need this much storage of this time frame, this much of that frame, this much of that time frame. And the other thing is, has your company or anybody else, or have you seen analysis that says how much is actually necessary with New York's general plan in terms of the amount of hydropower they're going to get, as well as the rest of it's going to transition to almost all renewable based on solar and wind? And I don't even know what the percentage between those two is, but say it's 50-50. Is that 6 megawatts peak power that they're talking about anywhere close to what's needed? And what is the time frame for gigawatt hours of total energy storage that's needed? Do you have any idea? Have you seen any estimates of that?
I've seen lots of estimates. They're all different. So I think the conclusion is that I don't think anybody really knows. I think that I think it's it's much more than 6, but probably not hundreds. It's probably, I think in the, I don't want to guess, but I think it seems that a lot of the estimates are coming in the 10 to 20 gigawatt hours or gigawatt capacity with I think in New York, based on the way the NYSO currently accredits capacity, I do think that it would be best to set the policies in gigawatt hours or megawatt hours in addition to megawatt injection capacity. Although I do think that it's implied based on the NYSO's rules for securing capacity that a 4-hour battery is for every megawatt of capacity, you're looking at a 4-hour battery. I don't think there's going to be too many battery projects that are built with a less than 4-hour capacity, because I think it's difficult to qualify for a lot of the products that NYSO wants batteries to sell or provide with less than 4 hours. So it would be best if it was in addition to megawatt hours, in addition to megawatts, also a megawatt hour rating. But I do think in New York that there is this implication that means there's a 4-hour, that batteries are a 4-hour duration. But I don't know how much is needed. I don't think anybody knows. I think one thing that, one of our kind of lead, the guys that sit in the dark rooms and model all day long for us, one thing he always reminds us of all of his modeling and others modeling is that, no one's ever done this before. Like no one's ever transitioned an electric grid from a thermal based generation system with unlimited, not kind of his theoretical, but just like practical in your head or, on site, unlimited fuel, right? A gas plant, we know doesn't have unlimited fuel, but from an operational perspective, you can plan it not have, there's as much gas as it can consume available through the pipelines for the most part. And no one's ever transitioned a system that was built on that type of management and of operation to one that's built on based on renewables, where you have to more actively manage it. I think what's really promising is that no one, when I first started doing renewables, I remember some of the first wind projects I built, no one thought that you could have more than 5% renewables on a grid at any given moment. And, last week, California theoretically ran on 100% renewables, and Texas routinely runs on 20 or 30% renewables. New York is, often well above 15% renewables at any given moment, and maybe even closer to 30 when you add in the hydro. And so I think people just don't know what's required to get there. And so I think it is going to be kind of these ever moving targets that people are setting. I think at some point there is going to be, hopefully hopefully we don't get to the point where there's this gap where we don't have enough storage and also don't have enough to retire. I think the worst case scenario is that the thermal generation retires too fast, and you don't bring enough renewables and storage on to keep the grid reliable, and then people lose faith that this transition can actually happen. And I think that's a risk that I don't think is going to happen, but I think could really slow momentum. But right now, I think there is this uncertainty, but I think the right people are open-minded about it, especially in New York. I think there's high-level political support for the transition, and I think the agencies that are responsible for making it happen, are there. Again, going back to a couple of years ago when I was developing projects, wind and solar projects, you go to meet with grid operators like NYSO or utilities, and they would be very dismissive because they never thought that renewable generation would amount to anything. And now, that's all they do. Like, all NYSO does is deal with wind, solar, and batteries. They don't do anything. That's all they do. And you're getting to the point where there are, mid-career professionals at those agencies where that's all they've ever known, right? Like, there are people at NYSO who are mid-level planners and mid-level administrators that have only done wind, solar, and batteries. That's been all they've ever seen NISO interconnect. And so I think that's part of the transition too. And I think those people are much more pragmatic about getting this to work, because they just don't even consider the fact that there's a grid that works with oil and coal and other things. And I guess the last thing I'd add to that is there's also kind of the uncertainty, right? We're in Texas, one of the utilities, Brazos Electric, that we're connecting to, told us, told us and a number of other folks that they had almost 2 times as many cryptocurrency applications to interconnect mining facilities as they did any other type of interconnection. So more than wind, more than solar, more than batteries. The number one thing that they are studying now, instead of new generation, is those types of facilities, which is, surprising to me, obviously.
Yeah, Peter, maybe I could add a comment here. You might want to talk to New York Best, Bill Acker. He's trying to act as an intermediary between the government, NYSERDA, and everybody else to optimize energy storage and the rules so you folks can make money.
Yeah, we're members of New York Best, and I'm actually speaking on a panel next week in Albany about the same thing. All of my great ideas of what they can do that they may want to listen to. Yeah, I think I'm on a panel next week about how to get things moving forward. I think NYSERDA in particular is a little disappointed that some of their incentive programs just haven't really hit the mark. And I know New York Best is working, and we've been working with them for a long time on policy matters. But yeah, they're a good group, and I think there's a conference next week in Albany about the future battery storage in New York, their annual conference.
Yeah, and FERC really sets the guidelines for this 4 hours, I think. So we may work with the feds on that.
Yeah. The FERC is is an interesting group because they do send a lot of these policies ultimately, and they're a partisan, they're a federal partisan agency, the Biden administration is turning over some of the FERC commissioners, but like a lot of kind of tertiary or lower agencies, they don't change policy the day the new administration comes in. There's lots of carryover, and especially with one-term administrations, it's kind of a mess. So, but the FERC has had lots of good things for storage. They've premiered some of the pay for performance policies that have enabled early projects. Our projects in Chicago are direct benefits from those pay for performance policies. But I think they can do a lot more, and I think the one thing that FERC could really do nationwide to help is create some capacity standards so that there are kind of these markets that batteries and can compete in universally across the different markets across different grids for capacity. But yeah, the FERC is a whole different. We're not big enough to have our own lobbyists at FERC, but I know we work closely with some of the ESA and some of the larger companies, and I have good personal friends at places like Nextera, and they have whole floors of people dedicated to lobbying the FERC, and not always to the things we want, but I think that they're doing a lot of good there as well.
Your Oakdale project, as I understand it, will be one of the largest projects in the United States, 480 megawatt hours. Is that correct?
It'll be definitely one of the largest in the Eastern Interconnect. I think some of the projects in California and Arizona and Nevada are catching up quick, and I would expect there'll be larger projects in California by the time we get built. But in New York for sure, and in the Eastern Interconnect, which is everything kind of east of Nebraska, it'll be one of the largest projects. Yeah, but they're a lot behind us. I think we were one of the first through everything, and we're not through it yet because we're still in the queue. But if you look at the NISO queue, I think for a long time developers thought that there wasn't that much economies of scale with batteries because it's just assembling a bunch of little pieces together. But I think the industry's learned, like solar, that there are, about a 7 to 10% economy of scale by doing larger projects. And it also allows
Peter,
for a little bit easier resiliency. Yep.
Peter, what plans do you have for training emergency crews like firefighters? I know there's a facility north of Albany where they train them every year. Does your company train these folks just in case something does go wrong?
Yep. So we for each of our projects, we as part of the building permit. So we've at Oakdale, for example, we're at what we would call kind of a standard design. So we haven't selected the final manufacturer. We haven't selected the final battery supplier. We've kind of sketched out what the design looks like, and as we get closer to construction, we'll start doing some of that stuff. And then once we select, the actual supplier, we'll work with them to finalize the emergency response plan and the exact systems within the facility. And we will review that. We have kind of 3 pieces to bringing in the project's kind of first responders. First, we'll work with the fire. I forget in New York what they're called. The fire. The person responsible for fire code. I think it's the code enforcement officer or the fire marshal. I forget the title in New York, but the person who's responsible for the code and planning, and we'll work with them as we design our protection systems and our detection systems and mitigation. So our projects there's protection, which keeps things from happening. There's detection that detects when something happens, and then there's the mitigation systems that prevent whatever happens from getting worse, right? So, we try as best we can to mitigate. And then if we don't mitigate, we detect and then respond. Work with them planning all those things. And then as the project is being built, we'll work with the manufacturer, of the supplier of the facility, and the installers, the suppliers of the detection and mitigation system. So usually the battery supplier has their own system that's directly related to the batteries, but then the project itself has a different a different provider that provides the fire detection system, and then they usually work with a project level fire suppression or extinguishment system. So we'll work with all of those to then do a desktop training, do the detailed response, like where are the trucks going to park, how are they going to come in, how do they get in the gate, all that kind of stuff. And then prior to energizing the project, we'll do a drill. We'll do an in-person training. So we'll set up different scenarios, bring the fire crews in, work with them to kind of walk through, like, what do you actually do when you show up? And then we offer that drill training once a year to fire crews or on request. Sometimes fire crews have either new people or they change. We had in Texas, one of our projects, they changed their mutual aid arrangements. So there would be a different, the primary fire crew were the same folks, but then the folks that would back them up was a different county. So we train them. The training is pretty easy. The training is to not enter the containers. There were some incidents early, several years ago in Arizona where some firefighters were injured. Those containers were the batteries were on the inside. So it's kind of like a mobile home, and you walked inside, there's an aisle that you walked down the middle of. So the fire crews, and they responded, were worried about there being people inside. And so they went through their procedures to check, and that caused the problem to get worse. As you'll notice in some of our pictures here, all of the newer systems that we're installing and the industry is really developing have no way of people getting inside anymore. There are no battery suppliers that I know of that provide systems that you walk into. They're all like this, where you open the doors on the outside and access the batteries that way. And so the nice thing about that is that you can tell the fire crews that there's no place for anybody to go inside, so they don't need to worry about somebody being inside that they need to go look for. And so, the procedure for these battery systems is to let them, let them do their thing and rely on the fire suppression systems to operate. A lot of these facilities will have external ways to supplement the fire suppression. So you can add, as the initial system kind of does its thing, you can add either more water or more chemicals depending on the facility. But really the primary role of first responders is to make sure that people stay away and to keep any fires or something from spreading outside the containers. And then we have a procedure with the manufacturers to declare containers safe. But that is usually, there was an incident in Phoenix just a couple weeks ago. It is the time from when an incident starts to when you start looking in, opening the containers and looking inside is usually measured in days, if not a week. There is that amount of stand down time between when something happens and you start looking into it. But there are, there are kind of durable sensors, and there's ways, our containers, these containers here in Texas, there's a drawing of where you are, where it's designed for you to drill in and start looking with a camera and that kind of thing. So, really since the incident, the first incident in Phoenix with APS and Fluence and LG, the industry's really taken fire safety to really be a core. And I think these next generation of stuff is going to be, far safer and to responders. And I think overall, even the Arizona facilities that had problems, there's never been any problem that I know of that has got anywhere close to affecting the public. Even the facilities where some firefighters got injured, they were directly fighting the fire up against the equipment, and nothing happened where it was outside the fence. So that's kind of a long-winded answer, I guess. But yeah, we do training. No special tools are needed. The projects operate, with 24/7 monitoring, and per NYSER rules, the projects do operate in fail-safe mode. So if they lose communications with our control center, they disconnect from the grid automatically. And even if they're working just fine, they're not allowed to operate without that oversight. So most of our facilities have at least 2, if not 3 separate telecom connections.
Baldy, I've had my hand up for
Yeah,
quite a
sorry,
Oh,
sorry,
sorry.
Jim. Go ahead.
while. Well, I'm ignorant about a great deal of this stuff, but so I have some very basic questions, and I don't need really complicated answers. But going back to balancing the loads between generation and load, are these actual humans that are doing this balancing, or are computers, or a combination of both?
No humans. Not at least not in real time. So there's when you balance the load, there's kind of two levels to that. The first is the real time. So right now, as we speak, you folks in New York and myself here in Minnesota, our respective grid operators, NYSO for you and MISO for me, are running control systems that are constantly monitoring the frequency of the grid across their system, and are comparing that frequency to the optimal frequency, which in the United States is 60 hertz. And as the frequency deviates from 60 hertz, they are in very rapid fashion issuing commands to different generators. For the most part, is still gas generators. Issuing commands to them to adjust their output up or down to try to manage that frequency back to 60 hertz. And depending on the system, those signals can be as quickly as every 5 seconds. So our project in Myersdale, Pennsylvania, receives a new set point from PJM every 5 seconds.
Wow.
And so that's how quick. So that's all automated. And that's how they manage the real time separation.
Is there a hacking vulnerability with these systems?
So the easy answer is probably not. The harder answer is, everything's connected. So, we do use, it is a private network to the grid operator, and there's all sorts of security built in, but there's multiple levels, both in our facility, but then, we're part of the grid operator's network. So anybody else who's part of that could have an intrusion and could get in. But for the last several years, there's been lots of work to improve the cybersecurity. So, all of our facilities have guardrail set points where, regardless of the command we get from the grid operator, there's controls physically at the site that prevent it from blowing itself up, for example, which has been some of the concerns that have been out there for older facilities. I think right now, to be honest, it's a little off topic, but I think ultimately the risk to the grid is not somebody sending odd commands to projects like ours. It's the more basics of just turning a bunch of stuff off and having that kind of thing. So I think we're probably still vulnerable to that type of attack, but we're not. It's not like someone can come in, and it'd be difficult for someone to come in and operate our facility in a way that would be damaging to us or the grid. But so that's the longer term planning of moving. That's kind of the frequency regulation is kind of like the second by second type back and forth. When you turn a light on, in theory, the grid's balancing that the light bulb you just turned on. Or probably more impactfully when your air conditioner kicks in, it's balancing that somehow. But more practically, like planned moving. So when in the grid for the grid operator, generators and load submit forecasts several times, but kind of the most accurate forecast is submitted the day before. So it's called the day ahead forecast. And so there is some planning that goes on, mostly automated, but with some of the grid operators, I think, discretion about how projects are matched or how load is met between the day ahead and real time. So there is some kind of more art to that, I think, than there is the pure automation. But a lot of it is predefined how that works, and I think a lot of it is left to these optimization algorithms, and I think that's going to get more advanced, because instead of just managing variable load, now you're managing intermittent generation from renewables, and you're managing variable load, and so you really need to kind of solve that problem in real time, with storage and other resources.
Thank you. Next, I got another question. So the graphic you've got up now, it's like the side of the mobile home, so to speak.
Yeah.
And you see the battery stack. Where are these units made?
So that's a good question. So these, I'll show up this slide now. This is a better one. So Powin Energy is a Canadian firm. So they assemble all of this, but the cells that they use are made in China. I would say that 80% of the battery cells used in utility storage are made in China or Taiwan, with the remainder made in Korea. And that's, there isn't a, that's just the answer. But Powin's a Canadian company, so they then the way Powin does it, and the way a lot of the other what they call themselves integrators. So there's the battery supplier, which is the firm that sends you the batteries, and then the integrator puts it all together for you. And a lot of the integrators are either based in for some reason Canada seems to have a lot of them, or the US or Japan. And so Powin's a Canadian company. They put all this together in Canada and then ship it down with the Chinese batteries inside.
Okay, last question. The power that the Oakdale system will be involved with, where does most of that power go?
That is the $1 million physics question. So there's two answers. There's the physics answer, which is more difficult, because energy will go wherever the nearest sink is. So wherever when we discharge a battery, those electrons are going wherever the physics brings them, which is the nearest place that they can reach where they can reach the lower voltage, like they're moving across the voltage spectrum from high to low. So that's the hard answer. Like no one knows. I mean, it is as far as I know, it's impossible to track the electrons. So no one, once they go through our meter, no one knows where they go. They just go in the system and they make their way out, but you can't track the individual electrons. So what everyone does, what we do instead is we financially track it. So we will settle. So when electrons move through our meter and turn our meter on our battery facility, the NISO is reading that meter. And then we, just like you settle your utility bill from when you at home, we settle our bill. It's a little more complicated, but we settle our bill with NISO. So we'll get one check a month or a week from NISO for all of our services, and then NISO bills those services out to the what are called load serving entities. So all of the companies that use load from NISO, which is the utilities, and in New York there's some grid choice, so you can choose your supplier. Those are all load serving entities. And there's the bills that we get from NISO will have hundreds of lines of billing codes that are all tied to different services, different things, different times, and they're allocated in different ways. The primary service that storage financially, the primary source of revenue is what's called capacity. And capacity is settled on a zone, in New York is settled on a zonal basis. And the zones are generally aligned with utilities. So we will, the simplified, if you had to pick where most of our money is coming from for these projects, it's coming from the customers within the zone we are located in. But it's regional, right? There's A through L zones in New York, so or A through J. Oh, L, I guess L. Sorry, L is after J. A through J. So that so you're still kind of within that group. So that's the medium length answer.
Okay, thank you.
Okay, I've got a detail question because I'm an engineer and I just can't help myself. I'm looking at this slide you have up right now, and I thought about asking this question earlier, but I didn't want to interrupt your presentation. You've got hundreds of these small little fans on each module rack that plugs into this huge rack.
Yeah.
Or drawers that plug into the rack, I guess I should say. Are each of these little individual fans monitored in case they fail? And there's probably chance of dust. You probably have a filter, maybe. I don't know if you do or not, but do you monitor for, or do you at least somebody manually check to make sure filters get replaced or cleaned out? And the other thing is, do you heat these battery systems when we have a cold spell of like minus 20 degrees or something like that? Do you have heating capacity to keep the thermal conditions optimal for this whole battery system too?
So last question first. None of our projects, even projects we're developing up here in Minnesota and in New York, they all are self-heating. We've never had a circumstance where there's been anywhere near a concern. It's always getting rid of the heat. Even in the coldest climates, it's always getting rid of the heat. And these operate on a similar to the way data centers, as I understand, operate, where there's a cold and a hot column, and they're all designed a little bit differently. But this project in Texas, for example, the cold column is in the middle, and the hot column is, I think you can see in this picture. So you can see in this picture, there's a orange, this orange, I don't know how to point on this thing. this orange, at the top of the container is kind of this orange bag kind of thing, right? That you can see kind of hooked to the top. And that's a curtain that kind of runs from the HVAC unit on the end and then kind of hangs down partway into the containers or partway behind the racks. And that's dropping the cool air in. And then the fans are pulling it through the, through across and through the battery modules, and then out. The door side is the hot side. I'm almost certain those fans are not monitored themselves. We do monitor temperature within the battery modules. So the battery module has several different temperature sensors that look at temperature directly, both the actual temperature, but then also the performance of the battery cells. We monitor and can see thermal issues with the battery cells with the voltage. In both those, the voltage our first warning when there's a thermal issue is usually from the batteries deviating from their what we'd expect to be the right voltage. So you'll see the electrical change and performance before you see an actual temperature change. And then we can shut down. I think on this project we can shut down at the rack level. So it's automated. So that if something deviates, it'll flag an alert for our techs. It'll shut itself down, and then it'll either somebody will go out there act proactively, or it'll be added to a list of things to look at during the next maintenance. We have these projects have a just like anything else. This is a multi-million-dollar piece of equipment. So there's a preventive maintenance cycle, which includes kind of all the things you mentioned and a number of other things. But there is a lot of filtering. I think the majority of the filtering that's done on these projects that I see and have heard of is on the intakes to the HVACs. You can see the seals here. I think the idea is that once this thing shut up, it doesn't really get opened up, very often. I bet besides opening photos like this, that these containers get opened a couple times a year. So I think it really is, once it really we're less about managing stuff inside of it and more just keeping things out.
Okay, that's good to know. I always worry about things like that. I have worked with electronic racks, and I know that these fans every now and then they do fail. And if you get enough failures, then you're going to start to have hot spots. And so anyway, that's just it's in my head. I can't help it.
Well, I mean, I can tell you that the most dramatic fire incident we've ever had at any of our projects was a cooling fan for interestingly enough, the fire notification panel.
Oh yeah,
itself started on fire, and set up all the stuff, but nothing to do with the batteries. Just a fan motor was the problem.
And I've got another question that's been sort of swirling around. Since this is one of the largest projects that we're going to have in the entire eastern portion of the U.S. grid, how is it that we ended up being the lucky ones in the town of Union, Johnson City area to get this project? How did you cite this, and how did that happen?
Yeah, so we well, first of all, I mean, I think we are the largest, kind of farthest along. But if you look at the NISO queue, there are a number of projects of similar size. One of our industry partner, one of our industry, I guess, competitors, but their Key Capture Energy is another big energy storage company in New York, and they have a number of similar size 100 megawatt, 150 megawatt projects. So I think we're just kind of the first in a line of folks. But what we do is we analyze the historical variability in pricing. So for battery projects, we're not necessarily going after the cost of energy at any given point, looking for the highest cost. We're looking for where there's the most variation in cost. And in this site, there's, I think partially because there's a couple of different transmission lines that come together in these two substations that are here. There's a lot of different flows of energy. It's not always flowing the same direction all the time. And it is one of the interfaces as you start to transition from what's called the downstate grid to the upstate grid, even though we're quite a ways away from, what I think is considered the downstate area. Electrically, you kind of start transitioning to it in this area. So I think what we've seen is that this substation here, there's a decent amount of pricing variability either throughout the day, throughout the year. And that's an indicator that energy storage can add a lot of value here. And that coupled with, we look at a lot of sites and, at the end of the day, it's a real estate development effort. So all the things that a real estate developer looks for, low cost land, things that are easy to construct, high likelihood of permitting are all things that we look at early on. It's like if you're citing a Dunkin' Donuts, you want to find the spot that people are going to stop and give you your business. But if you can't build your donut shop, you're not going to want to invest there. So it's a combination of, where electrically is the best place to put it. And then, once we determine substations that have potential, we'll look more at what I would call the traditional development elements, which are, land, permitting, environmentally, we do environmental screening to make sure there's not any environmental or cultural issues, all those kind of things that you expect a responsible developer does. That's kind of all part of our screening effort. So this site, it seemed to be a good fit for us, and and that's kind of why we pursued this specific site here. But the first thing we look at is substations and the historical price of power at each substation.
And that's analysis that you do yourself based on data that you can get from New York ISO?
Yep. Yeah. So it's a combination. We'll do kind of the last few steps of analysis ourselves. But there's various providers that will do a lot of the heavy lifting, going through, literally millions of points of data and distilling them down to, to kind of the information that you can analyze. And then our team will take kind of that processed information and start looking for what we think. There is some, they're part of it is a business. So there is some kind of discretion, in how you treat different indicators. It's, it is the energy market in New York and in most places is an open wholesale market. So it is a bid auction, for almost everything is an auction style network or option style marketplace, and everyone kind of competes, and it changes every day based on who's participating, who's not, and how people are bidding. So there's a lot of kind of that thought that we start thinking about when we first, look at developing a project is, how does it fit into our risk profile and our view of the revenue possibilities and all of that kind of stuff. But the source of that analysis is for the most part is historical data that we get, indirectly from NISO via some of these providers.
Okay. And just for your benefit, this business that's kind of diagonally to the below and slightly to the right, which is actually uphill, so it's north from your project site, is actually mostly a mulch business.
Oh, really?
Just so you know, it's landscaping mulch.
Nice.
So
yeah, I've only been to this area once. I think when you guys first reached out to us, I think you reached out to Erin Hazen, who was our staff developer for this project. And as people do, she took a different role, and we're in the middle of her just wrapping up getting a new person on board for our New York projects. We'll be starting, I think, next month. So I'm a little familiar with this. I think I went with her to one or two of the hearings, but I haven't spent a lot of time here besides I think one visit. But I'm very familiar with it. This is one of the bigger projects that we have under development. We're not. Most of the projects we're doing are 150 megawatts or smaller, and this is one of the more advanced ones. We do have one other similar size one in Pennsylvania that's probably about the same stage as this one, but these are kind of the we have been working on 20 and 50 megawatt projects, and these are kind of the next class of stuff we have are these 100 megawatt projects.
okay, and my wife just came up with a question. Why is your company named Glidepath?
Well, so I don't know. It's I think it has to do with one of our founders was kind general aviation pilot and kind of talked about, he was in the Navy a lot. And I'm not sure where it came from, his Navy aviation days or his personal pilot days. But I think the idea is that when you're coming into land at an airport, you want to kind of generally get in the area, and then you slowly start kind of coming in. And by the time, he'd always say, by the time the wheels hit the runway, you've got to be right on. There's no room for any mistakes. But until you get there, you're kind of moving around and stuff. And so as a developer, we're, like I said, we operate projects, but our initial business and our primary kind of historical business has been developing projects. And developing sites is a lot like that. You're kind of bouncing around, things change, you kind of slow down, you speed up, you're not quite sure where you're going, but eventually as you get closer and closer, there's less and less movement. And then, at some point it's all got to come together and you've got to land.
Okay.
That was kind of always his thing. I think that's abstractly what this logo is supposed to look like.
Okay, I like your explanation. I think that's good. Does anybody else have any comments or questions?
Yeah, I have a question.
Sure.
I'm asking you this since you're in Minnesota. I've heard about a company called Form Energy, which is advertising an iron air battery, which is claimed to have storage capacity of up to 100 hours or more. So a very unique kind of a thing. It seems to have backing from a lot of high rollers. Bill Gates is one of them. A tenth the cost of lithium batteries. And I think they were talking about putting in a pilot plant somewhere in Minnesota in 2023. Just curious if you have heard anything about that. I mean, they don't publish anything. It's a privately held company. Have you heard anything, through the grapevine about the likelihood of that succeeding or happening?
I've heard of it. I don't think I would have thought about it until you mentioned it, but I have heard of them. There's a couple of those. They all kind of phrase it differently, but zinc air, graphite air type companies that are, I vaguely follow what they're doing, but I think we're kind of, whenever someone's ready to sell something that's ready to go and commercial and is proven, we're happy to buy it. But we're not too involved, and and I'm definitely not involved anymore in the pilot stuff. But both Excel Energy, which is based here in Minneapolis, they have they're also in Colorado. They have a number of pilot projects, energy storage, and other projects scattered. And then there's another outfit, a cooperative called Connexus, and that's part of Great River Energy, and all they have been doing some energy storage. I know a couple of years ago, Great River did a pilot project where they used hot water heaters as an energy storage means, where they would proactively heat water for people, and they took control. I don't really know how that worked out, but I wouldn't. So it's not surprising that a Minnesota utility perhaps is doing that work, although I'm not really following it too closely. I did work on years ago on a wind project that was co-located with one of Excel's first batteries, a sodium sulfur battery. And I think the question earlier about heating things, that was kind of the opposite issue. That technology you had to keep really hot for it to work correctly. You had to keep the sodium molten, and it worked. My understanding is it worked well for a while, but then eventually the cost to keep everything heated was more than the benefits. It was consuming more energy than it was storing and discharging. And so I think they eventually shut that project down. But it was an interesting technology. There were these really like 15-foot tall stacks that had somewhere in there had molten salt. I never saw the inside of them. I just our project was next to them. But interesting idea. And there's been a lot of those different technologies that come and gone. I have a lot of sympathy for those developers. I worked for a compressed air storage company where we were working on a new novel technology for years and years and years, and spent a lot of money and time trying to perfect a technology to do energy storage that ultimately just did not work. You kind of get to the point where it works great in your AutoCAD drawing, it works great in your desktop model, it works great in your garage model, but then when you build one that's 2 megawatts in size, and our project was when you scaled it up to be 50 feet tall and I think we had big cylinders and all sorts of stuff. It turns out that some of the stuff is you just can't scale to that size, and didn't work. So I think there's a lot of folks that have done that, but there's also a lot of promising technologies and iterations that I think are going to get there. I think lithium-ion is, like I started out saying, I think is the go-to technology now, and I don't think anybody's building batteries that aren't lithium-ion for the next couple of years. But I would be surprised by the end of the decade if it's a different type of technology, and maybe a variety more differentiated between application, where maybe it's gravity storage for some different, for one type of application, that maybe the 4 to 10 hour or whatever longer duration is, and then maybe some different types of chemical batteries for shorter durations or something like that. The last thing I'll say on that is I know when we're designing our projects, we do put a lot of thought into when the batteries that we initially install have been kind of depleted. So after 5 to 7 years, they've like your phone, kind of run their course and just aren't effective anymore. Making sure that we're not, as best we can, not committed to having to replace those aged batteries with the last generation of technology. So we're designing our system so that you can disconnect the battery system and connect something different, and it'll still hopefully work. Which is that's not our secret sauce. That's how all the developers are doing it. But I think there's that much uncertainty where people are being a little more open-minded about what the future is going to look like.
Mm-hmm. Peter, might be worthwhile saying that you can have lower cost cells, but the energy density is 1/4 lithium-ion. Then the balance of the system is going to cost you a lot more land, more trailers, more everything else. So that.
Yep. Yeah, I know. I mean, this Oakdale project, it didn't work out well for us, but a lot of our other projects, we do have, several acres of additional land that we're acquiring for them with just that in mind. Either that, we might use something that is that takes up more space but is lower cost, or, I think one thing that we're expecting is that, that instead of replacing old batteries with new ones, we'll be augmenting and just adding more capacity. So leaving the initial batteries in place, but then adding more to it. And so we have been a little more, deliberate about the land, and it doesn't always work out in every site. But that is a good point that there is technologies that may have different densities. And I think they will be cheaper, because I think a lot of, at the end of the day, almost all of the batteries that are in these systems, at the heart of their design, are automotive cells. So that, the automotive industry has really driven, at least the cell manufacturer. Powin is a stationary company, so they're not doing autos, but the cells they use are auto, at least derivatives from automotive cells. And most of the other batteries are automotive cells, and there's a lot of pressure on energy density and having it as dense as possible. And for stationary applications like ours, that's not as big of a thing. So I will leave you with one kind of fun fact, is that in this picture here, you'll see these gray containers that are Jake Project that we built in 2015. And there is as much capacity in each one of these containers as there is in this green box here. So that's the advancement that the technology's made in just 5 years is that full container of batteries, which is about 15 minutes of capacity, is in this green box, probably a little less actually, in this green box now. So there is a lot of, and it costs about that project. So those projects for 20 megawatts and 15 minutes of capacity cost about $30 million. And this project in Texas, which is 10 megawatts, 10 megawatt hours, cost a little less than $12 million. So there's dramatic progress in both costs and technology that's happening. I think there's been a little bit of a detour on the cost, just like everything else in the world these days. But I think mostly we're pretty optimistic that that'll get back on track here soon. So it's coming.
Okay, thank you very much. And also thank you, Stan, for joining us too. I extended the invitation because I knew that you might be interested in, and you had some good suggestions and good comments and questions. So thank you. I appreciate it. And thank you, Peter, especially for giving a super detailed, rich presentation that gave a nice overview and then right down to our local project, which turns out to be more significant, even, you know, eastern half of the nation than I would have even imagined. So that's amazing. And I'm surprised that there isn't more press about it here. I invited our local WSKG, one of their reporters, to join us, and I guess maybe he either forgot or didn't have time or something, but I hope somebody covers this in some detail and writes up a good story about this, because the technology is available. We can do this. And New York is, like you said, one of the leaders in trying to make this happen. And yes, the planning needs to be better coordinated and better managed, and incentives need to be improved, but at least New York is trying to do it, which is more than many states. And nationally, boy, do we need to really get going. We're just down to about 7 or 8 years here to really reduce our emissions. We have this cliff, basically. We need to reduce. The slope keeps getting steeper and steeper the more years we wait to save a habitable climate. And projects such as this, of this scale, is what we need to make this happen quickly. Asking people to go vegan and to buy solar for their homes or buy an electric car themselves, that ain't going to cut it, because the entire economy needs to be transitioned. So I know you know this, but I'm just putting it here on the record because this is going to be recorded and maybe some other people might see this. I'm a little frustrated because we don't get higher attendance at these meetings. We try to make these educational as much as possible, and yet down to earth, understandable level. And I'm disappointed that our public isn't interested and our press is not interested. They cover sports every night religiously for roughly a 10-minute segment, which is just astounding to me with this national and international global crisis we have of climate change. And climate change just barely squeezes, a minute here or there. And it's really super frustrating. And I thank you for being on the side of trying to make things better. And also thank you to Stan and all the people that you are leading and doing research at Binghamton University. That gives me some hope. Thank you.
Well, thank you for the opportunity. I appreciate being able to share what we do. This part of my job is pretty good. I like sharing what we're doing to folks and educating them. It's much better than what I was doing a couple hours ago, which was staring at Excel spreadsheets, working on budgets.
Okay.
I like this, and I appreciate the opportunity. And my information's here. Feel free to reach out with questions. And if for some reason anybody's at the New York Best conference next week, I will be around, and feel free to reach out.
Okay, awesome. That's cool. Thank you very much. And thank you everybody on our audience for attending, and maybe just mention it to your friends, your relatives, that, hey, this is going to be available as a recording probably by the end of this week. And if they care about what's happening in New York State with renewable energy and the energy storage that's going to be enabling that transition, maybe they should check this out. They might learn something. It's, instead of watching some goofy show on TV, take some time and learn something and get involved, because the future is at stake. And if people don't influence their politicians, it's not going to happen fast enough. So thank you very much. Have a good night, everybody.